Okay. Let's get started. Let's get started. Hello. My name is Chandra. Good. Hello. Okay, good. Excellent. Welcome back, everyone. So this is Conf 330. This is lecture 5. Hi. Okay. This is lecture 5. So I don't have any major admin points to give you. So I think I'll just start with the lecture right away. I wanted to just remind you what we had done last class. So remember last class we had finished the DFA chapter by studying minimal DFA. And then we introduced this new type of machine known as the non-deterministic finite automata, the NFA. And just a reminder, the only real difference between the NFA and the DFA is that the NFA has the ability to choose, right? It has non-determinism, which means that its behavior isn't uniquely determined by the state it's in and by the symbol it's reading. In fact, it has multiple states to choose from to transition to. And at the end of class, I gave you this formal definition of NFAs, and I thought I'd sort of rewrite it here just in case you had missed writing it down at the end. I won't go over it. I'll go over it maybe quickly. So remember, like a DFA, an NFA is a 5-tuple. So it consists of 5 elements: the set of finite states, the input alphabet, the transition function, a set of start states. So in this case, it's not just a single start state, it's a set of start states, and a set of accept states. And the other major difference between a DFA and an NFA, along with the fact that it had a set of start states, was its transition function. In fact, that was the sort of major difference between the two. And so the difference was in the DFA's transition function. So you remember that in the DFA's transition function, you had the transition function taking a state and a letter, and then returning a single state, right? Because what it was doing was uniquely determined. In this case, for NFAs now, we allow the transition function to return a set of states, right? So these are the set of choices it has. Okay. And so to make this definition slightly more concrete, I'd like to give you an example. So suppose we have the following NFA, which hopefully will look familiar because it's an NFA that we saw last class. So this was the NFA that we had created or that we had designed to accept the set of strings ending in 0, 1, right? So hopefully you remember why, because the intuition here was that your machine would read through the string, and then at some point it would guess that your string was ending in 0, 1, and then it would just verify that. Okay. And so if we want to apply the definition to this NFA here, then we would say that the set of states is Q0, Q1, Q2, right? The input alphabet, in this case, let's say it's 0, 1. The set of start states, in this case, is a set containing a single state, right? It's a set containing the state Q0. The set of final states, again, is a set of a single state. In this case, it's Q2. And then the transition function is, again, going to look like a table. It's going to look like, in this case, a 3x2 table. But now the entries of the table are going to be sets of states. I'm not going to write down the whole table, but for instance, you could say that when the NFA takes Q0 and as input letter 0, then it returns Q0, Q1. Okay, and the reason for that is because if you're in Q0 and you read a 0, then you can either go back to yourself or you can go to Q1. And as another example, suppose you're in Q2 and you're reading a 0. Well, in that case, if you're in Q2 and you read anything, in fact, you're going to return the empty set, right? Because you have nowhere to go, whatever you read. So in this case, this would be the empty set. Okay. So hopefully that gives you a better feel of the definition. Now what I want to do is I want to talk about the extended transition function. So the extended transition function, delta star, and in this case, it's going to be the extended transition function for NFA. Okay, so we need to talk about the extended transition function because of the same reason that we needed to talk about the extended transition function for DFA. So for DFA, we had a transition function, and it would only take as input a letter. But what we want to do, we want to talk about the NFA accepting strings. And so strings are sequences of letters. And so we need a function that tells you if you're an NFA and you're in some state and you read some string, not some letter, but some string, which is a sequence of letters, then you go to this state. Okay. So that's why we need to talk about the extended transition function, because then we can formally talk about language acceptance. Okay, so how do we define formally the extended transition function for NFA? It's a recursive or inductive definition that takes as input a subset of states of your NFA, a string of letters, and returns a subset of states of your NFA. Okay, and the reason why in this case now we're talking about subsets of states, it's intuitive because we need to talk about acceptance for NFAs, and NFAs start at a set of states, right? So of course, if we talk about acceptance for NFAs, we need to talk about where does the NFA go from each of its states in the set of start states. And so we need to receive as input a set of states. So in particular, the set of start states. Okay, so how am I going to define this inductively when I need a base case? So suppose A is a subset of Q. So of course here I'm supposing that I have some NFA N Q sigma S naught O delta S naught F, right? So now I have some subset of states, right? And what happens in the base case? Well, the base case is for when you have some subset of states and you read a string with no letters. So in other words, you read the empty string. And in that case, the NFA says, okay, I'm reading the empty string, so I'll just stay at all of the start states, at all of the states I'm already at, right? Not necessarily start states. So that's the base case. Now, in the recursive case, I need to talk about a string which is not empty. And so this is a common trick, which if you looked at the induction notes, I use already. And so the common trick is if you talk about a non-empty string, W in sigma star, then you can rewrite W as XA, where X is some string and A is some letter. Okay. And now what we're going to do is we're going to define the recursive case based on this form of string. So it's going to be the same input set of states. So it's going to be some subset of states A. And as the string, it's going to be X. Okay. And so what does the extended transition function do in the recursive case? It does the following. So before I give you the definition, let me give you a high-level picture. So this is A, right? It's a set of states. So I have some states here. Now, what the extended transition function does in the recursive case, it says, given that I have as input XA, I'm going to read from each of these states in AX. So maybe when I read X, I go here. I also go here. Maybe when I read X, I go here. And maybe for the other two states, I just jam, right? I can't get to a state with X. And so now this is a set of states that are reachable from all of the states in A reading X. Now what I'm going to do is I'm going to say, okay, well now read this extra letter A. So for each of these sets here, I'm going to read an extra letter A. So I'm going to read a letter A here, here, perhaps here as well, here and here. And so what the extended transition function is going to return, it's going to return this set of states. Okay. So the way we write that down formally, it's very nice and compact. You take each of the states starting at A and reading X. Ooh, I'm going to need some more space here, though. Oh, good. Okay. So you iterate over each of these states. And what you do is you take the union of the states that can be reached when reading an A from each of these states. So in other words, you take the union of delta QA. And now remember, Q is like some variable going through some for loop. So you're going through each of the states in delta star AX, and you're taking the union of delta QA. And this is exactly what I've sort of described here. Okay. So any questions about that? Yeah. Yeah, so the union, you're taking the union over these sets of states. Yeah. Okay, so now that I've given you the definition of the extended transition function, we can actually talk about language acceptance. So language acceptance for NFA. Again, I'm going to start with a picture because I like pictures. Hopefully you do too. Okay, so I have my set of start states. Right, these are start states. I have how many I want, right? I could have 1, I could have 5, whatever. So the way we define language acceptance is, suppose I have some string W. What's going to happen is from each of these start states, I'm going to read W. My NFA is going to read W, and it's going to go to some state, right? Maybe it goes to more than one state. So maybe in this case here, I go to 2 states. Maybe in these 2 cases, I actually can't finish reading the string W, and so I jam, and so I don't get to read the whole string. But nevertheless, after reading the string W and starting from the set of start states, I have a set of destination states. So let's call these destination states. And so the way I define acceptance is very intuitive. I just say, well, this string W gets accepted by my NFA if at least one of these states is a final state, right? Makes sense? So if, for instance, this guy was a final state, so let's double circle it. This guy was a final state, so I have a final state in my set of destination states, then that means that my NFA accepts the string W. Okay, and so hopefully by now you've understood why I needed to define the extended transition function the way I did, because it allows me to talk exactly sort of in this scenario. Okay, so how do I talk about this slightly more formally? Again, we're supposing we have some NFAN. So I don't want to keep rewriting the 5 tuple, but suppose I have some NFAN and some string W. Then we say that W is accepted by N if and only if when you start at the start state, at the start states, the set of start states, and you read W, you have at least one common element with the set of final states. So the way we can write this in terms of set theory is you take all the destination states, right? These are the destination states. And you take the final states or the accept states. These are the accept states. And you check if their intersection is non-empty. If their intersection is non-empty, that means that they have at least one common element. So what you'll do is you'll say, take the intersection and then check that this is not empty. And that's how you formally define a NFA accepting a string. And so you'll notice that the intuition I was giving you last class where I was saying, oh, well, you can think of a NFA as accept, okay, something weird going on with the lights. Okay, yeah, it's a ghost. It's the ghost of, no, I shouldn't have said that. So what was I saying now? Damn it, stupid lights. What was I saying? Someone remind me? Oh, yes, thank you. Okay, so when I was talking about NFAs last class, I was saying, an NFA to accept a string, it reads that string, and if there's one successful computation, at least one successful computation, then it accepts that string. If there isn't any successful computations, then it rejects it. And so really what you can think about formally is the NFA is trying all the possible computations, right? It tries all the possible computations, and then it checks, is one of my destination states a final or accept state? And if yes, then I accept the string. If no, I reject it. Okay. And so that allows me to talk about the language accepted by an NFA-N. So it's the set of strings. It's the set of strings such that you start in the start states and you have a common element with the set of accept states. Okay. So I feel like so far things have been hopefully very intuitive and clear. Okay, good. So let me just give me 2 seconds. Let's take this example again and reuse it. So for those of you who are not using an iPad and are handwriting your notes on a piece of paper, I apologize. But what are you going to do? So suppose this was again an NFA-N. What I want to do is I want to illustrate the extended transition function and the notion of acceptance with this particular NFA. And so to do that, let me just pick some string. I know that to talk about acceptance, I need as the input to my extended transition function, I need the set of start states. So in this case, that's the set containing Q naught. So I take the set containing Q naught, and I take 0, 0, 1. So what's going to be returned here? Well, it's going to be all of the states that are reachable from each of the states in this guide. In this case, I only have one state, and so it's just the set of states that are reachable from Q0 reading 0, 0, 1. So in other words, if I look at my machine, if I'm at Q0 and I read 0, 0, 1, then I can either stay here, so I read a 0, I read a 0, I read a 1. So I can stay at Q0. Or I could read a 0 here, read a 0 here, then read a 1 here. And then I would end up in Q2. And you'll notice that Q2 is an accept state, which means that I accept the string 0, 0, 1, which works out with sort of the intuition I gave last class. So 0, 0, 1 is accepted. Yeah, because the set of destination states has at least one accept state. In this case, it has the only accept state. Okay, now let's quickly look at a rejection scenario. Suppose I'm at state, so suppose I'm starting at the set of start states. In this case, again, it's just Q0. I'm talking about the same machine, right? And I read 0, 0. Well, I can either stay at Q0, right? I read a 0, I read a 0. So I stay at Q0. Or I read a 0, and then I read a 0 here, so I go to Q1. But neither of these are accept states, right? And so I reject the string 0, 0. Okay, good. So that's what I want to say about the extended transition function. I'm going to use it immediately to prove a theorem. Usually when you give definitions, it's to prove things. But before I do that, I just want to note some facts about delta star, one of which you have to use to prove the thing I'm going to prove. And that's going to be that so suppose I have an NFA, right? And I have some subset of states and some strings XY. Actually, suppose I have two subsets. Okay, because there's two facts. So keep my bases covered. The first fact is if I start at a set of states A and I read the input string XY, then this is the same as starting at A, reading X, and then from there reading Y. Okay, so this fact I'll prove in a separate note. So proof in an extra note. I won't have time to do it here, and it's just a really boring induction. So you already seem very bored, so I don't want to bore you even more. Maybe you'd be less bored if I was Prakash, but I don't can't do everything. Really? 2 laughs. Okay. So the other fact is what? Is if I start at a set of states, A union B, and I read an X, right? Then this is the same as saying, well, I'll read from A, X, and I'll read from B, X, and take the union of these two. Okay. So these seem very intuitive, and they are, and it's just very boring proofs by induction. However, this one is a boring proof by induction that you'll need to do in your assignment too, because I'd like for you to be bored. Okay. Yeah. Yeah. I couldn't hear the last part. Yeah. No. No, it can include Q1, sort of logically, because this string ends in 1, and you can never end in 1, right? Because if you were to end in 1, yeah, because you need to read the full string. Yeah. Is that a question? Yes. You're asking a question for him? Oh. Yes, but for the second case, it's 0, 0. Then it reads all. So in other words, you didn't even have a question. Okay. Good. All right. That means it's clear. Any other? Yeah, one more. Yeah. Yeah. So when a string ends, you just don't include the state in the set. Because this is a set of destination states where you read the entire input string. Yeah. I'll take more questions after. I have to move. I'm sorry. I'll move on. But you can ask after. Okay. So the next thing I want to do is I want to talk about something that we talked about at the beginning, or sort of towards the end of the last class, which was NFAs are really these sort of convenient machines to write to write down language acceptors, but they're no more powerful than DFAs. Okay, so in other words, the power of DFAs is the same as the power of NFAs. And so I'll state that slightly more formally in this theorem. So THM stands for theorem. People are whispering, and that's very distracting. Excuse me, could you not whisper? Thanks. Sorry, it's very distracting for me. It might not be distracting for other profs, but it is for me. So I have a theorem here. The family of languages accepted by DFA, which I'll denote L sub DFA, is exactly the same as the family of languages accepted by NFA, which I'll denote L sub NFA. So in other words, the family of languages accepted by DFA, which I'll sort of write slightly more explicitly as taking every possible DFA, so M is some DFA, and you take the language accepted by M, right? So this is a set. Well, this set is exactly equal to taking the some NFA N and taking the language accepted by N, which I use to denote L sub NFA. Right, so this is the set of all languages accepted by DFA, any DFA you can think of. And this is the set of all languages accepted by NFA, any NFA you can think of. And it turns out that these two things are exactly the same. Right, so in other words, NFAs are sort of only very nice in terms of notational convenience, but they don't sort of give you more power. So now I have to actually prove this because otherwise you won't believe me. So the proof of this, because I have a set equality, right? I'm saying that this guy is equal to this guy, and these two things are sets. I need to do a set equality proof, which requires a sort of double inclusion procedure. So in other words, I need to show that the family of languages accepted by DFA is a subset of the family of languages accepted by NFA, and the family of languages accepted by NFA is a subset of the family of languages accepted by DFA. Okay, so that's, I need to do this to prove this result. So the first part of this proof, and I think saying that this is a proof is sort of might upset mathematicians, so I'll write that this is a proof sketch. So otherwise people might get mad. Okay, so the first part of the proof is very easy. Why is it very easy? Let's see. Let's try that. Yeah, Louis, yeah. Yeah, very good. So this direction is very easy because take any DFA. Well, a DFA is just an NFA that doesn't use non-determinism, right? And so, of course, any language accepted by a DFA M will also be a language accepted by an NFA N, namely the NFA that just looks like that DFA, but never uses non-determinism, right? And so we could just say a DFA is an NFA which does not use non-determinism. So it chooses not to use non-determinism. Okay, so that direction was easy. That's nice. The second direction will be slightly less easy, but will be fun because you get to see a new proof technique, which is nice. So for this direction, it's less obvious. What you need to do essentially is you need to take any arbitrary NFA-N and somehow convert it to an equivalent DFA-M, right? And by equivalent, I mean that the languages accepted by the two machines will be exactly the same. So to do this, what I need to do is given an arbitrary NFA-N, what I need to do is I need to create an equivalent DFA-M such that the languages accepted by both are the same. Okay, so how am I going to do this? Well, how do I convert? This is an interesting question. How do I convert an NFA into a DFA? Well, so you remember that what an NFA is doing, right, is it has a bunch of possible choices, and the way it's really going through its computation is it's just trying all of the possibilities, right? And so instead of talking about NFAs in that way, what we can say is, well, DFAs are just equivalent machines where you take some state and you just try all of the possibilities all at once, so simultaneously. So what does that look like? What the heck does that mean? Suppose I have some state Q. So suppose this is an NFA_n, and I have some state Q, and when I read the letter A, I can go to 3 places. So I can go to P1, or P2, or P3. So the idea is that in the equivalent DFA, what's going to happen is you're going to have the same state Q, but now when you read A, you're going to create a state which encodes the fact of going to either P1 or P2 or P3, right? So your DFA is going to encode information, right? That's what we've been talking about so far. DFAs and NFAs, their states encode information. In this case, this particular DFA, which is equivalent to this NFA, is going to take these states and encode them all in a single place. Right? So this state is going to encode the possibility or the choice of going to either P1 or P2 or P3. And so you'll notice that I'm saying or a lot. And whenever you talk about elements sort of in a sort of disjunctive fashion, that typically leads to talking about sets of those elements, right? And that's what we're going to talk about in a second. So really formally, what you're going to do is you're going to say, well, I know that when I'm at Q and I read an A, I go to either P1 or P2 or P3. Well, then what I'm going to do in my machine M is if I'm in Q, and sort of a slight caveat, it's going to be if I'm in the set containing Q and I read an A, then I'm going to go to the set containing P1, P2, P3. Okay, so this is what the conversion algorithm is going to look like. So, okay, I missed a page there. Let me add a page so I can actually formally construct it. So now this is the idea. What's the formal construction? Formal construction. So when I say formal construction, I mean, how do I formally construct a DFA from some arbitrary NFA_n? So I know nothing about this NFA_n other than it's an NFA. Right? So this method is also sometimes known as the subset construction method, which you'll see makes a lot of sense. It's a good name for it. So given an NFA_n, which I will explicitly denote this time as Q sub n, sigma sub n, delta sub n, S sub n, F sub n, right? So there's subs to make it clear that these are the elements of this arbitrary NFA_n. Okay. So what I want to do is I want to construct an equivalent DFA_m, which looks like Q sub m, sigma sub m. Okay, you get the point. Delta sub m, S sub m, F sub m. Okay, so this is just to make it explicit that these are going to be belonging to this DFA_m, right? So how is this construction going to look like? What I'm going to do is I'm going to first assign for the set of states of my DFA, I'm going to assign it the power set of the set of states of my NFA. Right? So Q sub m is going to be assigned the power set of Q sub n. Right? So this is exactly what I was saying before, right? My DFA, each of its states is encoding the possibilities that my NFA can take. Right? So this is exactly taking any combination of states you can go to. Any combinations of states you can go to, that's just another way of saying a subset of Q sub n. Then the alphabet, we're going to say is exactly the same. the start state of my machine M. What is a logical start state for my machine M? Yeah, good. Very good. So it's S sub n, which like works out, right? Because S sub n is a subset of Q sub n, right? Which means that it belongs to Q sub n. Right? Very good. Now, this one might be slightly more tricky. What is a logical way of defining F sub m? Yeah, good, very good. So the set of accept states of my DFA M are going to be all of the subsets of Q sub n that contain at least one accept state. So that's exactly this guy, right? So it's the set of all subsets of Q sub n such that Q and F have at least one common element. The last thing I'll do is I'll define the transition function delta M. So delta M is going to be a transition function. And so if it's a transition function of a DFA, then it has to look like taking some input from Q sub n, Q sub m, and some letters from sigma, and returning a state from Q sub m. Now, what is the actual explicit definition of delta M? Well, suppose I have some state in Qm. Well, this is exactly equivalent to having some subset of Qn. Right? So I have this as the parameter of the states, right? The state parameter of delta. And I'll take some letter as the sort of letter parameter of delta. Now, if I have delta M, which takes a state B and a letter sigma, then what should this return? Well, it's going to return exactly what I said here, right? It's going to take all of the states in the set of input states, and then take all of the destination states and union them together. So what this is going to do is it's going to iterate over all the states in B, right? Because remember, even though B is a state in my DFA, it's a set of states in my NFA, right? So I'm allowed to iterate over the states in B. So I iterate over the states in B, and I take delta Q sigma for each of those states. Okay. And this is the construction of an equivalent NFA. So for this to be very rigorous, we need to prove that. So the next step would be to show that L of M, so M, which I just constructed, is exactly equal to L of N. But I think I'll spare you, and I'll post an extra note. Okay. To make this a bit clearer, I have an example, but are there any questions before I do that? Yeah.
It is not a question, but sort of the defect act is it supposed to be accent?
Yes, yes, thank you. Thank you very much. Excellent. Thanks. Yes. Yeah. So this is a power set, yes? This is the okay, why? Okay. So this is the power set of Q of n, right? So the idea, that's sort of the whole idea of the proof, the reason why you're assigning the set of states of your DFA to the power set of the set of states of your NFAs, because your DFA wants to consider all of the possibilities that your NFA will take. So all of the possibilities means your NFA is in some state, and it can either go here or here or here. So then you take all of those possibilities and you make that mistake in your DFA. And that's exactly what this is doing. This is just sort of a formal law. Yeah.
Can the little sm be equal to sm? I thought in how DFAs was only one start state and then.
Okay, that's a good question. Yeah, yeah. That's a good question. So the question is, why can I assign little s of m to big Sn, right? Because the question is, well, aren't you supposed to have only one start state in your DFA, right? And the answer is absolutely, yes, you must have exactly one start state in your DFA. And that's exactly what you have here, because, oops. If you have S of m being assigned S of n, right, then this is a subset of Q of n, right? So it's a single subset of Q of n, right? So then you have a single subset as the start state of your DFA. So again, you only have a single start state. Yeah. One more question. Yeah, Owen. Yeah.
So is the DFA more than NFA unless that NFA is itself an NFA?
So is a DFA inherently more minimal than an NFA?
I'm just thinking about the attribute of the two going three separate
Yeah.
states.
Yeah.
So the DFA sort of squishes them all down.
Right. I see. I see. Well, yeah, it's difficult to answer that question because there's no notion of minimality for NFA. So that question is slightly ill-defined, but maybe we can talk about it more during office hours. Maybe we can like work through possible question. Let me just go through an example and then, okay. So to make things slightly more concrete, what I'd like to do is I'd like to give you an example of a subset construction, because writing it out would take 10 minutes. I'm not going to do that, and I have something prepared. So again, I'm sorry if, well, in this case, even if you have an iPad, you're in tough luck. So this example here is of the NFA that we've seen already twice. So this is like the running example. So this is our NFA. And the idea was, can we use this method that I just explained to convert it to a DFA, right? So remember, my NFA had this as its set of states, this as its input alphabet, and so on for all the other parameters of the 5 tuple. And so the idea in the subset construction is you take the set of states in your NFA n, and you take all of its possible subsets, right? So in this case, because I have 3 states in my set of states of my NFA, I have 2 to the 3, 8 subsets for my DFA. So when I construct my DFA, it'll look something like this. So I haven't reproduced all of the subsets here because, for instance, the set containing Q2 is actually an unreachable state. Because when you work it out, it turns out that there's no way to get from the set of start states, which in this case is the set containing Q0, and going to the set containing Q2. Okay, so like I said before, this is the start state. So like someone pointed out, there's only going to be one start state because this is the unique subset of Q that contains all of the start states, right? So in particular, that's Q sub naught. In this case, I used Q sub naught instead of S sub naught. Okay. Then in terms of the final states, the only final states for my DFA is going to be the set containing Q0, Q2. And that's because that's the only reachable state that has at least one accept state in it. So in this case, it has Q2. And so you see that this guy has Q2. So there could be other accept states, but they just wouldn't be reachable. So that's why I haven't written them. And let's just check that this sort of transition works. So this mapping between the transition of NFA works. This mapping between transitions of NFA and DFA works out. So if I'm in my NFA, right? So let me go here. If I'm in my NFA and I'm in Q0, you see. Right, this doesn't, I see. So if I'm in Q0 or Q1 and I read a 0, and in this case, because I have a set of states, let's talk about the extended transition function. Then what this is going to return, we already saw this. Well, actually, no, we didn't quite see this. It's going to return Q0 and Q1, right? So it's going to return the set containing Q0 and Q1. So what should happen in my DFA? In my DFA, if I'm at the state Q0, Q1, and I read a 0, then I should go to the state Q0, Q1, right? So does this happen in my DFA? Oh, it doesn't. It's because I made a mistake. Right. So my bad. It should have been like this. So trust me on this. It should have been a self loop on Q0, Q1. So if I'm in my DFA and I read Q0, Q1, and I read a 0, then I go back to Q0, Q1. Okay. And so an exercise for you just to check. So it's possible that some of this is slightly confusing because it's a bit abstract, but an exercise for you is design a DFA that accepts the language of strings over the alphabet 0, 1, where those strings end in 0, 1. And what you'll notice is that the machine you'll create will, in fact, exactly be this machine. And this doesn't always happen. Sometimes when you convert an NFA to a DFA, you create redundant states. But in this case, that won't happen. So in this case, this doesn't happen. You don't have any redundant states here. And so the DFA and the converted NFA to DFA will match. So sorry about the typo here, though. Okay, questions about this? Yeah. Yeah. So let's just make this a bit clearer. So this was a garbage collector. So the garbage collector in this case is the state representing the empty set. Right? So the empty set, whatever it reads, the state representing the empty set, whatever it reads, it'll stay at the empty set. Right? So yeah, these two guys are unreachable, and there's other states that are also unreachable. For instance, this guy is also unreachable, right? I just didn't want to sort of crowd the page because that would make it 8 states. Did you have a question? Oh, yeah. Yeah, I guess you could. Yeah, you could talk about minimality in that sense. Yeah, that's right. You could talk about minimality for NFA in the sense of not being able to create an NFA that has a small number. That's true. But you just can't talk about yeah.
I know you've already covered it, but could you go over like the start state, like and like with this example?
Let me check if I. Yeah, okay, I could do that. I'll try to quickly go over that. So the question was about why is the start state in the DFA? Could you phrase the question? Sorry.
Yeah, the question is basically like if you did like I'm equal to
Yeah.
I'm saying like this example, like
Right. Okay. Yeah. So in this example here, the start state is the set containing Q0, right? But that's exactly the set of start states of the NFA. So there's just a one-to-one mapping. Yeah. That didn't take all that long. Yeah, last question, yeah. There's sets of states of the NFA.
Yes. Yes.
Wait, if you get a zero where? If you get a zero where? Yeah, which start state? Okay, yeah.
Get it through. In the NFA, there's no order.
Yeah. Yeah. Well, I'm not, I think you said except, which I'm not quite sure why you said except.
You get a zero, you get these zero, 2 0 or 2 1, so they are. Is that why they are intercept?
Yeah, exactly. Yeah. So if you're in the NFA and you're at Q0 and you read a zero, you either go back to Q0 or you go to Q1. So that's why in the corresponding DFA, right? If you're in the set containing Q0 and you read a zero, you go to the state that represents the set containing Q0 and Q1. Yeah, exactly. Does that make sense? Yeah. Okay, good. All right, excellent. So I think I'll move on for the sake of time. There's so essentially the result that we now have. So this result that I'll write down again is that the family of languages accepted by DFA are the same as the family of languages accepted by NFA. And so in fact, that means that the family of languages accepted by NFA are exactly equal to the family of regular languages, right? Because by definition, the family of regular languages is the family of languages accepted by DFA. And so the implication of this result is that to prove L is regular, you can do the first thing that we saw last class and the class before, which is to construct a DFA M such that the language accepted by M is L, and then of course prove correctness. But now there's a new feature that's been added, which is you can construct an NFA N such that the language accepted by N is L. And of course, you need to prove correctness for this guy. We haven't really talked about proving correctness for NFA. We won't give an explicit example, but really the idea would be pick some string in L, show that there always exists a path in the NFA that starts at some start state and ends at some accept state, and then pick some string that's not in L and show that that can't happen. Okay. And so an exercise for you, which would have been difficult had we only talked about DFA, but now is relatively easy. Suppose I have an input alphabet and some language over the alphabet sigma. What I want you to do is to prove the following statement. If L is finite, so it has a finite number of strings, then L is regular. Please don't shout out the answer, because this will also be in assignment 2. Okay. Okay. So that's all I want to say about traditional NFAs. I want to talk about another equivalent machine which adds some more notational convenience. And that's going to be the NFA with epsilon transitions. Okay. So I'm going to give an informal definition and then show an example like I always do. So what is the definition? Informally speaking. So an NFA with epsilon transitions is an NFA which contains, or I guess which allows epsilon transitions. Well, that's the most useless definition I've ever seen. What is an epsilon transition then? Epsilon transitions are transitions, so state transitions, labeled with the special symbol, in this case, epsilon, that allow the machine to change state. So in other words, to transition without reading any letter from the input tape. So NFAs with epsilon transitions are NFAs. So they are computational machines, very simple computational machines that as input take strings and as output say either accept or reject the string. But now they have this extra feature of allowing epsilon transitions. Okay? And these epsilon transitions are transitions between states that allow the machine to transition from one state to another without actually consuming any input. So they're allowed to transition for free. So let's see an example, otherwise things will remain very obscure and confusing. So consider this following example, which is actually taken from Dexter, but I like very much. So consider this following NFA with epsilon transitions. So this is going to take a bit of time to write down, actually. So this state has, this NFA has 6 states. And altogether, they look like this. Okay, so this is the NFA with epsilon transitions. Now, how does this thing actually work, right? So what do I mean by the machine is allowed to transition without reading any input from any letter from the input tape? So essentially, the other way to think about it is these epsilon transitions are free transitions. You're allowed to transition from one to the other for free, right? It doesn't cost you anything. So for instance, if you have as input the letter B, so well, let's not say the string containing only the letter B. Then of course, because this is an NFA, it's allowed to have multiple choices, and in this case it does. So let's try to work through some of the choices it has. So of course, it's always going to start at one of the start states. In this case, there's only one. And perhaps in this case, the NFA with epsilon transitions just decides to immediately read this transition B. So it reads the transition B, and it goes to Q1, and it decides, okay, I'm done. I'm very lazy today. I don't want to keep going. So it stops at Q1, right? Q1 isn't an accept state. And so this is a failed computation. So now maybe the NFA is going to get slightly smarter, and it's going to see that it has epsilon transitions, and it's going to try to use them. So how could it do that? Well, here's one example. It could, again, read the B and go to Q1, right? So it would read the B and go to Q1. But now let's say it's slightly more eager to keep going. And so it's going to take this epsilon transition. Whoops. It's going to take this epsilon transition for free. So it doesn't cost it anything, right? It can do this because epsilon transitions, you're allowed to transition from one state to another without reading a letter. So it takes this epsilon transition and it goes to Q2. Now it can't go to B because it's already read a B. But it can use another epsilon transition and go to Q4. So it can use another epsilon transition and go to Q4. But then at that point, it's stuck, right? Because at that point, it's at Q4, and it can't read this B because it's already consumed the B, right? So once a machine consumes a letter, it can't go back and read it again. That's the characteristic of finite automata. And so once it's at Q4, it gets stuck. And again, because this isn't an accept state, it's a failed computation. Now, do we think it can succeed? Yes, someone nodded. Good. So let's see how it can succeed. So instead of the machine being super eager to read this B, it's going to say, let's be slightly more patient. So instead of immediately taking this transition B and consuming the B, it's going to, for free, read for free go from Q0 to Q2 with this epsilon transition. So with this guy. And then it's going to think twice of reading this B, and it's going to say, well, no, actually, what I think I should do is go to Q4. So again, it's going to go to Q4. And now at this point, it doesn't really have much of a choice, but actually that's good, because at this point, it has to consume the B. So it has to consume the B, and it ends up in Q5, which is an accept state. So it's read all of the input string, it's ended in an accept state, and so that's a success. Okay, and so that means that B is accepted. And just in general, the acceptance conditions, so the acceptance conditions for NFA with epsilon transitions are the same as NFA. They're exactly the same. In other words, it has to start at a start state, read the entire input, and then end in an accept state at least once for at least one of the computations. The only additional thing that it's allowed to do is it's allowed to use these epsilon transitions to transition from one state to another for free, right? So without reading any of the input table or any of the letters on the input table. Okay. Yeah, give me 1 second. So if you work this out, so I'll leave this as an exercise. You can check that the language accepted by this machine, oh, I should have called it, what did I call it? Let's call this N, is the set containing only 3 strings, which are going to be B, B2, and B3. Yeah, question.
Basically, my question is, just to make sure, if you can keep that file, do you have to? So if you have like,
But remember, when an NFA is return, right? But an NFA with epsilon condition is an NFA. It's trying all the possible computations.
yeah, like if you have a 0 epsilon Q1, will I always end that Q1 or can I just stop you?
You can stop at 0. Yeah. Yeah.
Is the set of languages accepted by NFAs the same as the set of languages accepted by Epsilon NFAs?
What do you think? The question was, is the family of languages accepted by NFAs the same as the family of languages accepted by NFAs with epsilon transition?
Intuitively, it feels like the same.
Yeah. Why is? Could you talk maybe a bit about that intuition?
Well, you're not looking at the state.
Yeah, good. So in other words, you could conceivably design a equivalent NFA which considers where it goes when it reads the letter and when it reads the letter and then uses these epsilon transitions. And that's exactly the proof for it. Very good. Yeah.
What the organization there is that you can do is possible.
Ah, very good. Ooh, that's a good question. Right, okay, that's a very good question. So the question was, what happens if I have, do I have time to do this? Yes, I do. Okay. What happens if in my NFA with epsilon transitions, I have something like this, right? So the question was, doesn't this give you an infinite loop? So in fact, the answer is no. This doesn't give you an infinite loop because, well, there's 2 reasons. The first one in general is there are no infinite loops in FAs. There will be in Turing machines, but there aren't in FAs. The other reason is, more specifically about this example, once the machine starts at Q0, right, it can read this epsilon as many times as it wants. It's always going to stay at Q0. So effectively, the computation is ended, right? Because it's not going anywhere, right? So effectively, it isn't really an infinite loop. Yeah, but that's a very good question. And we'll talk a lot more about infinite loops in the latter half of the class. Maybe I'll do an example and then I'll take the question. So what I want to do now is I want to give you another example / exercise in which I design an NFA with epsilon transitions. And you'll see that NFAs with epsilon transitions are actually indeed very convenient. So the question is to design an NFA with epsilon transitions that accepts the following language. So this language is going to look like the following. Okay, so the language is essentially a sort of divided into 3 parts. Really, you can think of it. It starts with a sequence of Bs, then it's a sequence of BAAs, and then it's a sequence of As where, in particular, you need an odd number of As. So if you try to do this with a DFA or a vanilla NFA, for a DFA, it'd definitely be a pain. For an NFA, it might be slightly less bad, but it's very, very easy for an NFA with epsilon transitions. So why is that? Because like I just said, you can sort of decompose this language into 3 parts. You can start with the part that's a sequence of Bs. So what's a machine that recognizes a sequence of Bs? Well, it's a machine with a single state with a self loop as B, right? With transition B. Then what's a machine that recognizes a sequence of BAAs? Well, that's a machine that reads B, A, and then goes back with an epsilon transition, right? So I can read as many BAAs as I want, right? 1, 2 BAAs, 3 BAAs, as many as I want. And the last one is a sequence of A's where I have an odd number of A's. So how do I do that? Well, because I need an odd number of A's, this is very similar to my parity bit checker. But instead of sort of filling it up with a bunch of A's and B's, I only need to think about the A's because I only care about a sequence of odd number of A's. And so I'm going to have 2 states. One is going to represent an odd number of A's, and another is going to represent an even number of A's. Right, so in this case, let's say that this represents an odd number of A's, and this represents an even number of A's. And so, of course, because I care about this guy, I'm going to make this an accept state, right? And now I need to join these things all together. How can I do this? Well, I know that whatever string I have, it could start with the pattern any number of B's. And so I'll make the start state be this guy. Then it can read a bunch of B's, right? My machine reads a bunch of B's. And then at some point, it notices that it's the beginning of the pattern for BAs, right? In that case, for free, it can transition with this epsilon transition to this machine. So then this machine reads as many BAs as it wants. And then once it's done doing that, it can, again, for free, transition to this machine, which then reads an odd number of A's. Okay. And then this is a machine, an NFA with epsilon transition that accepts this language. Okay. I think you had a question. Okay. Oh, what's the point? Yeah, now you see. Yeah, try doing a DFA for this. Yeah. Yeah.
Middle part, like just getting rid of one state time.
Yeah. I just really wanted to use that function. But yeah, you're right. Yeah, so that's a very good point. You could have also just done, that's a good point. You could have also just done this. And yeah, that would have worked just as well. Yeah. Yeah, one more question, Mish.
So these are we about like normal energy stuff like this, right? You're reading, you have a problem, you read this, you make this, right? Then you end up transforming this into that's like.
There's no good algorithm. The best algorithms are sort of usually exponential, which is yeah, annoying. For some special cases, they can be polynomial, but sort of O and Q. Yeah, it's not great. but yeah. But the idea is, this is very compact, right? So for hard disk, it's not too bad. And then you assume that you have, infinite time, right? So then it's very easy to convert. Because you're assuming that you can do this sort of, in a sort of, back-end process, right? Okay, one more question. Yeah. Yeah.
Like, link multiple machines that you could take together.
I would say that's a use case of that. But the epsilon transitions are just transitions, right? From one state to another, that allow the machine to go from one state to another without actually creating work. But yeah, this is a use case. Yeah. What do you think? So, oh, okay, 10 minutes, good. So what I want to do, yeah. So I just want to state formally another theorem, which just tells us that these machines are actually equivalent. So I'll write this much more compactly than for the first theorem. And so it's that the family of languages accepted by NFAs is exactly the same as the family of languages accepted by NFAs with epsilon transitions. So again, this is a set equality statement. And so to prove it, you need to prove it by double inclusion. You need to show that this is a subset of this, and that this is a subset of that, right? And so to do that, there's one easy direction, and then there's one hard direction. So the easy direction is this one. Whoops, not. So why is this easy? Yeah. Yeah, because remember the definition, the informal definition of NFAs with epsilon transitions is that they're allowed to use epsilon transitions. But of course, that means that if you don't use them, then that's okay, right? So NFAs are NFAs with epsilon transitions without any epsilon transitions. Okay. The second direction is slightly trickier, but not all that tricky. And it has to do with a previous question, which is if you have some NFAs, some NFA with epsilon transitions, how do you convert that to an NFA? Well, it turns out that you can convert that to an NFA. That's why this statement is true. And so I'm not going to prove this because that would take long. But I will post a note again. So I have lots of notes to post for you. But the intuition would be if in your NFA with epsilon transitions, you have something like this. So in your NFA with epsilon transitions, if you're at P and you read an A, you can either go to Q or go to Q and then to R, or go to Q, then to R, then to S. So the idea in the conversion procedure is to consider all of these epsilon walks or epsilon paths, and then integrate them into the sort of newly constructed vanilla NFA. So the idea is to convert this then to something like this. Okay. And to do this formally, you have to talk about epsilon closures, but I don't want to do that because it's not really interesting. There's another more interesting way of proving this actually, and that's using homomorphisms, which I unfortunately don't think we'll be able to cover, but I'll post supplementary material in case you're interested. Okay, so then the result we have here, is that the family of languages accepted by DFAs is exactly the same as the family of languages accepted by NFAs, which is exactly the same as the family of languages accepted by NFAs with epsilon transitions, which is exactly the same as the family of regular languages. Sound like a news reporter. Okay. All right. So then the implication is that to prove that L is regular, so that a language L is regular, you can, one, provide a DFA and then prove correctness, two, provide an NFA and then prove correctness, or three, and this is new, so this is very exciting, that's why there's an exclamation mark, you can provide an NFA with epsilon transitions. Okay. So let's see, what should I do? I'm ahead of schedule, so I'm debating what I should do. I could take a question. Yeah?
Are one of these like easier than the other mostly?
Yeah, that's a good question. And let me answer that question by giving you an exercise. So prove that the language, so the question was, are one of these easier to construct? It depends on what language I'm asking you to prove is regular. So in this case here, I'll let you think about what's easier to do. Okay, so yeah, I don't think I'll solve this because I'd like to give you one more definition before we end class. But if you look at this problem, so try it out, you'll see that it might not be feasible to do a DFA for this, and it's probably not feasible to do an NFA for this, but an NFA with epsilon transitions, that's probably very doable. So it depends on the language, yeah. And then, so then the classic answer is you kind of need to practice a bit. Yeah, yeah, Louis. Yeah, it's a pain, because that's why I didn't want to talk about it. But you have to talk about epsilon closures. So there's one way to talk about to formally talk about NFAs with epsilon transitions. You need to talk about epsilon closures, which are epsilon closures are if you're at a state, then the epsilon closure of that state is the set of all states that are reachable with any number of epsilon transitions. So you have to define that, and then that allows you to talk more formally about NFAs. No, I'll post something you'll see. Okay, so before I end, I'm not quite sure why people are packing. I still have 2 minutes. So this sort of concludes the chapter of talking about computational machines. So I'll get to you at the end. We've talked about DFAs, about NFAs, and about NFAs with epsilon transitions. So these are all the sort of FAs that we'll talk about. And so we've just seen that they're all computational equivalent, so you can use them all to prove that a language is regular. What we're going to do next is we're going to talk about closure properties. So, yeah, closure properties of regular languages. So I won't have time to formally define this, but informally, closure properties, hopefully if you've already sort of heard of these, is, for instance, if I say something like L1 and L2 are regular, then L1 union L2 is also and will always be regular given that the premise is true. Okay, so we're going to look at these next class, and what we're going to do is we're going to prove them constructively. So we're going to say L1 and L2 are regular, which means that we have 2 machines which accept them. So we'll have 2 machines which accept them. For instance, we'll have M1, which accepts L1, and M2, which accepts L2. And then somehow, using our nice tricks of non-determinism and of epsilon transitions, we'll show that we can combine these machines together to create a machine M, which accepts L1 union L2. And then we'll do that for several of the other language operations we've already seen. For instance, L1 concat L2, L1 star, L1 complement, L1 intersect L2, and so on. So there will be a bunch of these. They'll also be in your homework. So make sure to come on Tuesday. Thanks very much. Have a nice weekend.